We are in chapter 4 where we are discussing bending. This is the 33rd session overall. In the earlier session, we discussed general eccentric loading, and here we look at some examples on that issue. We also start discussing unsymmetric bending. This is a general overview of the sessions covered in the first 4 chapters. As we can see, we are on the last leg in the chapter on bending. This session and the next session are the last sessions involving straight beams. We then look at curved beams, and finally we summarize the whole. Here we have an I section with a load P applied as shown. The load P is eccentric to both the axis of symmetry, and initially we do not specify the y and the z directions. Let us look at the moment that the load P will cause. So about the vertical axis, this will be the direction of the moment. About the horizontal axis, this will be the direction of the moment. We choose the axis so that the direction of the moment vector aligns with the axis. So the direction of the vertical and the horizontal axis is chosen as shown. We earlier discussed that the z-axis has to be 90-degree anti-clockwise to the y-axis. So the y-axis and the z-axis is designated here as follows. Now in this problem, we are not given the load P. We are given the allowable stress in compression and the allowable stress in tension, from which we find the value of the load P that can be applied. That is the maximum value of the load P. We have been given the dimensions of the I section, so we know the area of the section and we can find out IZ and IY. Since we now know the direction of Y and Z, we chose the axis so that the moment applied would be positive. So we find the positive moment applied about the z-axis and the y-axis. These moments are with respect to P, and substituting the moments and P in the equation of stress, we get an expression of sigma in terms of P and also Y and Z. Here we have the expression of sigma that we obtained in the earlier slide. Sigma was given in terms of P and the ordinates Y and Z. We have earlier been given the maximum allowable stress in compression and tension. So using the maximum allowable stress in compression, we'll find out a value of P. And using the maximum allowable stress in tension, we'll find out another value of P. Out of these two values of P, whichever is lower gives us the required value. Now consider a section taken as shown. Let us consider that the points A, B, C, and D are the furthest points from the axis of the section. So here the cross section is shown with A, B, C, and D. The moment acting on the section is also shown along with the axial force acting on the section. By inspection, we can see that the stress in A will be the maximum compressive stress. Consider this moment about the z-axis. It will cause a compressive stress at A. And consider the moment about the y-axis. It will also cause a compressive stress at A. Also, the axial load will cause a compressive stress at A. We can add up these stresses, which will give the stress at A in terms of P. To prevent failure, that stress has to be equal to the allowable compressive stress, from which we can find a value of P. This value of P is the maximum value that can be applied without compressive failure. Now consider the point D. It will be subjected to the maximum tensile stress. We can equate this stress to the allowable stress in tension to get a value of P. That value of P is the maximum value that we can apply without tensile failure. Comparing these two values, we see that the maximum value that can be applied is the value related to tensile failure. So the maximum P that can be applied is this value. We have a rectangular section on which an eccentric load P has been applied. The load P has been applied at a distance y dash from the horizontal axis of symmetry and a distance z dash from the vertical axis of symmetry. Now let us consider that y dash and z dash are variables. We are required to find out an area within which P can be applied so that the stress on a section such as A, B, C, D will be compressive, and the area has to be found within this quadrant. Now, the load P, which is eccentrically applied, is equivalent to a centroidal force and two moments about the axis of symmetry as shown. As earlier, we choose the z-axis, the same direction as the moment vector of this moment, and the y-axis in the same direction as the moment vector of this moment about the vertical axis. This y and z axis is corresponding to the stress. Here y dash and z dash are also variables. So we take y dash and z dash axis, which relates to the position of P as shown in figure 2b. So we have two sets of axes, coordinate axes. Now Consider this moment about the z-axis. This quadrant then will be under tensile stress, and the maximum tensile stress will be along this line. Now consider the moment about the y-axis. Again, this quadrant will be under tensile stress, and the maximum tensile stress will be along this line. So the point A will have the maximum tensile stress due to both moments. Since we want this section to be free of tensile stress, we'll find out condition at which the stress at the point A, which has the maximum tensile stress, to be 0. So we'll find out the locus of the point P first, at which the stress at the point A is 0. Now this moment is a positive moment, so mz is equal to p into y dash, and the moment my is p into z dash, which is also a positive moment. Y dash and z dash is taken as per this axis. The moment of inertia about the z-axis is p h cubed by 12, and the moment of inertia about the y-axis is h b cubed by 12. The area of this rectangle is b into h. This was the algebraic equation we obtained for stress when the loading was eccentric. As earlier mentioned, we want the situation where the stress at A is 0. So we will find out the stress at A first using this equation. At A, y is equal to minus h by 2 and z is equal to b by 2. So we substitute appropriate values in this equation to get the stress at A. The load is minus P, the area is PH here. MZ is Py dash and IZ is PH cubed by 12, with Y is equal to minus H by 2, from which we get this value. Because there's a minus here and Y is also given as minus H by 2, this value is positive. Similarly, we substitute My, Z and Iy to get the third expression. We then take P divided by PH out of this expression and have this part minus 1 plus 6y dash by h plus 6z dash by p within the bracket. Now sigma at A is 0, which we are considering, and as such this expression within the bracket has to be 0, which gives us this equation. This is a linear equation between y dash and z dash. It gives us the locus of the point where if P is applied, the stress at A will be 0. So we substitute y dash is 0 and we get z dash is equal to P divided by 6, which we plot here. We then substitute z dash is equal to 0 and we get y dash is equal to h by 6, which we plot here. Since the variation is a straight line, we join these 2 points using a straight line. So this line gives us the locus of the points at which P can be applied so that the stress at A is 0. If the load P is applied within this shaded area, then this rectangle will be in compression. If the load P is applied outside this shaded area within this quadrant, then part of this rectangular portion will be in tension. Earlier, we were commonly using this formula to give the stress at a point subjected to eccentric loading. So the loading was fixed and the geometrical parameters were also fixed. We took different points with coordinates y and z and we could find sigma. So the variables were y and z, which could be given as per the coordinate axis chosen. One would note that the situation here has changed. Now y and z at the point A is fixed, so they are no longer variables. The stress at A is known, so this is also fixed. The loading, the P is still fixed, but the moments vary. And now the parameters have become yz, y dash and z dash. So these 2 are the variables. The problem here is the same as in the last slide, except that the load P is applied to a different quadrant. We'll try to find out the area in which P can be applied within the quadrant, so there's no tensile stress in a section such as ABCD. Load P is equivalent to an actual load and 2 moments about the y and the z axis as shown. The moment about the z axis causes tensile stress in this quadrant and the maximum tensile stress at P. The moment about y similarly causes tensile stress in this quadrant and the maximum tensile stress at P. We do not want tensile stress, so the maximum tensile stress at P has to be 0. We have to find out the locus of P within this quadrant, which corresponds to the stress at P being 0. That locus will give us the portion within this quadrant in which if P is applied, then the stress in this cross section will be compressive only. We see that the coordinate axis chosen here is the same as the coordinate axis the last slide. So this is the coordinate axis related to stress, and this is the coordinate axis related to moment of load. Till now, we have chosen the coordinate axis so that it coincides with the moment vector, but here it is not the case. Here, if we consider this moment and the z-axis direction, then the moment vector does coincide with the z-axis direction. But if we consider the y-axis and the moment vector direction, then the moment vector direction does not coincide with the positive y direction. As a result, the moment associated with the z-axis is positive, but the moment associated with the y-axis is negative. Here the moment about the z-axis is p y dash, and the moment about the y-axis is p z dash. P z dash is a negative moment. To understand this, consider that p acts at a distance 3 along the z axis. So it's acts somewhere here. Then the negative moment is minus p into 3. However, based on the coordinate system chosen, z dash is equal to minus 3, or minus z dash is equal to 3. So minus p into 3 is given as p z dash, which is a negative moment. We earlier found that the stress is given by this formula. We earlier found out Iz, Iy, and A, and here we have found out Mz and My. P here is compressive, so we substitute these values in this expression. As per this coordinate, the ordinates of the point B is minus h by 2 and minus b by 2. Substituting these values, we get the expression for sigma at B. For the second term in the right-hand side, we have two negatives, so the expression is positive. For the third term, we have one negative and one positive, so the expression is negative. Taking out P divided by P, which we have this expression. Now for this whole section to be in compression, stress at P has to be 0, which means that the portion in the bracket has to be 0, from which we get an equation of y dash and z dash. This equation will give us the locus of the point P, for which the stress at P would be 0. Substituting y dash is equal to 0, we get z dash is equal to minus b by 6. And substituting z dash is equal to 0, we get y dash is equal to h by 6. So we have plotted minus b by 6 and h by 6. Since this is an equation of a straight line, we have joined these 2 points using a straight line. So within this quadrant, we have now found an area where if P is applied, the stresses at in the section will be compressive. If we look at this coordinate axis, then till now we have considered load to be acting in the first quadrant and in the second quadrant. From what we have learned, we can use inference to determine the areas in the third and fourth quadrant where if load is applied, the section will be in compression. Consider these 2 points minus b by 6 0 and 0 minus h by 6. We join these 2 points by a line. If the load is applied anywhere in this line, then the stress at C would be 0. If the load is applied anywhere within this region, then the stress on the whole section will be compressive. Similarly, we can find a line here in the fourth quadrant, considering the stress at D to be 0. This whole shaded region is called the kern. If load is applied anywhere within this shaded region, then the whole section will be in compression. If the load is applied anywhere along these 4 lines, then the opposite point would be in zero stress. If the load is applied in the region outside this kern, then at least part of the section will be in tension. We have discussed symmetric bending analysis in detail and briefly mentioned unsymmetric bending analysis. Here we'll give a short general description of symmetric analysis in order to move on to unsymmetric bending analysis. Consider this beam which has an axis of symmetry and to which a positive moment has been applied. Let us take a section CDEF. We have determined the neutral axis and the variation of stress in this section. Let us consider the portion to the left of the cross section. The portion to the left is in equilibrium and a 3D object needs to satisfy 6 equations. 3 of these equations involve forces and 3 involve moments. Now there are no forces or stresses acting in the Z and the Y direction. There's also no moment acting about the x-axis. So we need not worry about these 2 equations and this equation. Using the relation summation fx is equal to 0, we found out the position of the neutral axis. The relation summation mz is equal to 0 could be given in this form. This relation led to the lecture formula, and we could give the variation of stress at the section. Hence, we are left with this equation. There's no moment acting about the y-axis, and we get this expression. There was a moment m acting about the z-axis, so we had m here on the right-hand side, but here we have 0. For a symmetrical section, understanding this equation is straightforward. Since the y-axis is also the axis of symmetry, the moment due to the left and right of the y-axis, both in the top and the bottom of the neutral axis, are equal. So there's no net moment acting due to the stresses about the y-axis. Now consider an unsymmetric section to which a moment has been applied about the z-axis. We assume that we know the position of the neutral axis of the z-axis. The stress variation will still be linear. Then sigma x at a distance y from the neutral axis will be given as sigma x is equal to sigma max into y divided by y1, where y1 is the maximum distance from the neutral axis and sigma max is the corresponding stress. Substituting sigma x in equation 3, we get this expression. Here, sigma max and y1 are constants. So for the equation to be satisfied, integration yz dA over the whole area A has to be 0, or the product of inertia has to be 0. Hence, if we choose the axis y and z so that the product of inertia is 0, we'll have my as 0 and a finite mz value acting. In order to better understand what we have just found out, we'll look at this problem from a different perspective. So instead of looking at the problem from the perspective of external moments applied, we'll look at the problem from the perspective of the neutral axis or the axis of zero stress. Previously, we have considered cases where the section was symmetrical and there was a moment about two perpendicular axes acting along with an axial force. If there's no axial force acting, then for such a case with two moments acting about two perpendicular axes, would be able to find out the position of the neutral axis. Here, however, we have an unsymmetrical section. We'll work in reverse, where we assign the position of the neutral axis arbitrarily. So that z-axis here is taken as the neutral axis. We'll then work backwards to find the moment. With an unsymmetric section, the variation of stress is still linear. Consider an element dA. Then the moment that the stress acting on the element causes about the z-axis is minus sigma x y dA. And the moment that the stress acting on the element causes about the y-axis is sigma x z dA. If we consider such elements about the whole area and integrate, then we'll be able to find out the moment about the z-axis and the moment about the y-axis that these stresses create. So the moment about the z-axis is given by this expression, and the moment about the y-axis is given by this expression. We substitute sigma x is equal to minus y into E divided by rho. Then we find that the moment that these stress create about the z-axis is E divided by rho into Iz, and the moment that these stresses create about the y-axis is minus E by rho into Iz. So we arbitrarily chose a z-axis as the neutral axis, and we found that the stresses acting would create a moment mz and my, which are given by this expression. Due to the stresses, these are the internal moment acting on the section. It needs to be pointed out that the mz and the my we have found by considering an arbitrary neutral axis are in a given proportion to each other. Earlier we considered the z-axis as the neutral axis or the axis of zero stress. The corresponding stress distribution was examined. It was found that due to this stress distribution, there would be a moment acting about the z-axis and also a moment acting about the y-axis. If the stress distribution resulted in an internal moment about the z and y-axis, then there must be an external moment mz and my. The external moments mz and my and the internal moments would keep the portion of the body in equilibrium. As mentioned earlier, we considered symmetrical sections subjected to moment about both the axes as well as an axial force. So, with a symmetrical section, if there were moment acting about both axes, we would be able to find out the corresponding position of the neutral axis. Here the section is unsymmetrical and we have worked in reverse. The neutral axis at a section depends upon the moments acting apart from the geometry. So, if we predetermine a neutral axis, then we can find the moments which are related. And due to them acting, the line of zero stress is formed. We earlier discussed that the moment my would be zero if we choose axis for which product of inertia is zero. Earlier we had considered symmetrical sections with only mz acting. The flexure formula giving the distribution of stress was found out for only this one moment acting. Axes for which the product of inertia is zero are called the principal centroidal axis. These principal centroidal axes are found to be 90 degrees to each other. So, among the two principal centroidal axes, if we considered one axis as y and the other as z, and we applied mz, then would be able to use the flexure formula, which was derived for one moment. The axis of symmetry in a symmetrical section is analogous to the principal centroidal axis in an unsymmetrical section. We can look at the issue in another way as well. In figure 2, let us consider the z-axis and the y-axis as arbitrary. The z-axis, as before, is considered the neutral axis. Then in general, one would think that the moment about the y-axis caused by the stresses on the left and the right will not match. So there would be some net moment acting about the y-axis. Now let us keep on rotating these two orthogonal axes. We rotate till the moment about the left and the right of the y-axis are equal to each other. So there's no net moment acting about the y-axis. Then the y and the z-axis are the principal centroidal axis. We'll next find the axis at which the product of inertia for an unsymmetrical section is 0. This is done by transformation of axis with the origin as the centroid.